So just to give everybody a quick background on VSP, we started in the 1970s as just a gasket distributor. Starting in about the mid 1990s, we began hiring engineers and developed our own internal testing capabilities at our headquarters in Richmond, Virginia, as well as elsewhere, to kind of become not just a distributor, but also an engineering partner for folks that we supply parts to. One of the benefits of that is we supply for just about every major gasket manufacturer. So having our own engineering department and our own internal testing capabilities allows us to be a reliable third party in terms of what materials we recommend. It also has allowed us in the last 25 years to develop some of our own products in specialty areas where we see that there's a need for them, which brings us to FRP flanges. We've talked about the pros and cons of these, corrosion resistance, cost, lightweight. In terms of cons from a sealing performance standpoint, it's really the strength that presents some sealing issues. Namely, the fasteners are always going to be low strength fasteners, and you're going to have very limited torque values that are typically given by the FRP flange manufacturer, but are going to be much lower than the values that you would use on similar size metallic piping. The other aspect of it is for most non-metallic piping, it's going to be flat face as opposed to raised face. And so it requires a full face gasket to protect the OD of the flange from rotation. If you try to use a ring gasket on an FRP flange, you're going to rotate that flange, which typically means you're going to crack it. Those two things combined, low bolt load and a lot of gasket area, results in very low gasket stress, which is the main sealing issue when it comes to all non-metallic flanges. Historically speaking, this has limited you to elastomer gaskets for non-metallic piping. The reason being that elastomer gaskets can seal down to, generally speaking, 500 psi of gasket stress. In terms of sheet gasket material, the next best material would be a premium expanded PTFE, in which the minimum seating stress, generally speaking, is 3,000 psi, so 6 times higher than that of an elastomer gasket. The issue with elastomer gaskets is mostly on the mechanical side. So anybody who uses rubber gaskets know that you can tighten a rubber gasket up. It will pass that initial leak check just about every time because it is a great sealing material, but you give it a day, a week, sometimes even an hour, it will relax and lose at least 50% of its bolt load shortly after tightening it up. So while you can get a reliable seal on startup, typically they don't have a very long service life because eventually you will lose that bolt load, you'll lose torque, and you'll either have loose bolts or you will just have a leaking flange connection. The problem with hard gasket materials, like I said, any standard sheet cut material, so expanded PTFE, filled PTFE, graphite, compressed non-asbestos, the minimum stresses to seal for those are much higher than what you can achieve with a standard FRP flange. That picture there is obviously not FRP, but another non-metallic flange where I believe they were using an full face expanded PTFE gasket. It was leaking, and they did what any good mechanic would do, and they kept increasing the torque until it stopped leaking. But before they got to that point, they cracked it like you see there on that picture. So the good news is, in recent years, there have been innovations to gaskets specifically targeted at low bolt load scenarios like FRP flanges. And this is a good graph before we get into that. So this is for standard NPS class 150 sizes. On the left side there on the table, you'll see the maximum recommended torque from this particular FRP flange manufacturer. On the graph, that is the generated gasket stress for each of those sizes based on those torque values. That yellow line there is, there's a little bit of overlap, so you might not be able to see the legend, but the yellow line is the minimum stress to steel for an elastomer gasket. So you can see while All of those, you're generating above that 500 PSI mark. Like I said, after a certain period of time, that actual applied gasket stress on an elastomer gasket is going to drop. And it is very close already in most situations to that 500 PSI mark. So odds are, shortly after startup, a lot of these will start to leak. For reference, there is a line for the 3000 PSI mark, which you see you're not even really getting close to for expanded PTFE. And I couldn't include the other sheet materials on this graph because it would have thrown it out of whack and you wouldn't have been able to see anything. Because we have new gasket styles now that are targeted at these low stress to seal, we want to be able to evaluate them, A, to ensure that they work in the first place, and B, be able to compare them relative to one another. The issue is that most of the standards that already exist for gaskets out there are for metal flanges. ROT is typically the standard used for evaluating gaskets, room temperature operational tightness test, and EN 13555 is the European test for evaluating gaskets. Both of these stresses that are applied to the gaskets and the internal pressures are both much higher than what you'll see on a plastic flange. So the values that you're getting from those tests, you can't extrapolate them to an FRP flange. So VSP has developed our own testing protocol to, A, like I said, qualify that these can be used with an FRP flange and seal in the first place, and B, be able to compare them relative to one another in terms of their gas leak rate. The various gaskets that we used for our test, obviously first is, I would consider it to be our control gasket, just your standard full face elastomer gasket. In this case, I believe we use a 60 durometer EPDM gasket. To be honest, in our experience, between 60 and 70 or 50 and 75 durometer sheet cut gasket material, there's not a whole lot of variation in their performance in terms of hardness. Once you go down into super soft elastomer gaskets like 40 durometer or harder gaskets like 90 durometer, you start to see a difference, but most sheet materials are going to be between 50 and 75. We also tested a reduced area elastomer gasket. So this is a design that VSP has that obviously can be used on any different gasket material. The intent is to keep the overall OD of the gasket the same as the flange at the bolt holes. That way you're not going to rotate the gasket. It's still going to absorb that load so that you're not cracking, but we're taking away some of the gasket in areas that don't do any sealing, namely outside and between the bolt holes. All that really serves to do is increase the gasket area and decrease the gasket stress. So by removing that with the same bolt load, you can achieve higher gasket stresses. The next gasket we tested was a filled PTFE material that is manufactured with a raised hexagon face. So you can kind of see it there, but there's ridges all along the gasket that effectively point load the gasket so that you're not sealing across the entire face. You're really just sealing along those ridges. So we tested both the full face and a reduced area. The next is a molded expanded PTFE. So this is your premium expanded PTFE material. The difference between this and your regular sheet cut is it's molded with a very thin impermeable outer layer. And it's molded on the ID, and that goes all the way out to the OD. What that does is, the problem with expanded PTFE is there are air gaps in the matrix of the material. So you need to get enough compression on that to close those air gaps. Otherwise, you get leakage through the gasket matrix itself. With the molded expanded PTFE, because you have that thin impermeable outer layer, it's still soft like expanded PTFE, but you're not going to have gas leakage through the gasket itself. So that allows you to, while as expanded PTFE, your minimum is 3000 PSI. For this material, typically you'll say 1500 PSI. So we did this in both a full face and reduced area. The next is a expanded PTFE gasket in a reduced area design. However, on the ID of the gasket, it has a fully encapsulated corrugated metal insert. What that does is twofold. One, when you compress the gasket, most of your stress is going to be applied to the peaks of that corrugation. So you're thereby increasing the effective gasket stress because you're concentrating it on a smaller area. What it also does is that metal insert acts as a spring. So any sort of external loads, whether it be thermal cycling or vibration, where you would typically lose load in another even virgin expanded PTFE gasket, that spring live loads the gasket, so you're going to maintain that gasket stress throughout your external loads. The next one is a full face elastomer gasket with, on the ID, you have a molded thin PTFE layer. I believe it's virgin PTFE. It may be glass filled. But what that does is it eliminates some of the chemical compatibility concerns with using the wrong elastomer, because theoretically the outer material, what the elastomer is, does not matter because that does not see contact with the fluid. All that is contacting the fluid is that encasing PTFE layer. It also has molded peaks, so it achieves basically the same concept as the gasket before, where you're concentrating that load. So while as a regular PTFE, you need a certain amount of stress, this way you're concentrating the load on a smaller area to increase the gasket stress. And last is a virgin expanded PTFE. This is another reduced area design. This is separate from the other one where you are cutting out the areas that effectively aren't sealing or aren't supporting the flange. Here you have the ID is a raised face, which is doing all of your sealing. The area in between, technically when you compress it, you're not going to compress down to that, so that's not doing any sealing. And then on the OD, you have another raised face that protects the flange and also protects or prevents the ingress of any foreign material into the flanges themselves. We don't see this a whole lot, but there are applications, whether it be underwater applications or in particular dirty environments where you can't have any buildup, even though it's outside of the process itself. They don't want any buildup in between the two flanges, so having that sealing ring out there prevents that. We used a 3-inch 150 FRP flange. For those familiar with flanges, the 3-inch is one of the more problematic sizes because of the limited amount of bolt load. That's because 1, 1.5, 2-inch, and 3-inch all use 4 bolts. When you go to a 4-inch, you jump up to 8 bolts. You see the same issue with 8-inch flanges, because when you jump from 8 to 10, you go from 8 bolts to 12 bolts. So 3-inch, 8-inch, 12-inch, they're all underbolted flanges. So we figured worst case scenario, that is what we'll test. We had two FRP pipe spools bolted together with a gasket in the center, and then on either end a stainless steel blind flange. On one end we had the stainless steel blind flange with an NPT fitting, which was then threaded to basically our pressure assembly, which we used nitrogen for this test. What we did was, before we put the final fitting on, filled it up to about 1 inch from the top with water, bolted the final blind flange on, turned it back horizontal, let it sit for 30 minutes to make sure that there were no leaks, which ideally there would not be any leaks under no pressure and basically just the head pressure from the liquid. After which we connected the nitrogen assembly to begin the liquid leakage portion of the test. And I'll also know that we use 35 foot-pounds and coated fasteners per the manufacturer's recommendations. So the first test, the liquid leak test, basically the pass-fail to see if you can use these with an FRP flange at all. We derived this from ASTM D5421, which is the specification for FRP flanges. It does include guidelines for pressure testing the flanges themselves to ensure that they can withstand 1.5 times their rating pressure. Because this was the closest we had, and it already had a good framework as far as pressure testing the flanges themselves, we use this as the basically the base to develop our liquid leak test on. So a lot of this here you can find in that standard. We just, instead of targeting qualifying the flanges, we're qualifying the gasket that goes between the flanges. So what we did was raise the internal pressure to 100, 200, and 250 psi with 1 hour dwell times in between, checking for any liquid leaking out of the flange. After the 200 psi stage, we dropped it down to 225, which is 1.5 times the rating pressure, and left it for 7 days. Again, checking for liquid leaks, and that all comes from the D5421 requirement, that 1.5 times system pressure for 168 hours, which is a week. If leakage was detected at any point from any of the flanges, we stopped the test and we would install a new gasket, increasing it from 35 foot-pounds to 40 foot-pounds, which is the maximum recommended from the FRP manufacturer. As you'll see later, you'd think that 5 foot-pounds would not have much of an effect on the sealing stress, and you would be right. For the gaskets that passed the initial liquid sealing test, the next stage was our gas rate leak test. So going back to this slide here, you can see that we have a manometer here to measure the pressure differential over time. So we rerouted the nitrogen back through that manometer for the gas leak rate test at the 225 psi. And using that pressure differential over time, we're able to back calculate the mass leak rate of nitrogen out of the entire assembly. And we also divided that then by the OD of the gasket in millimeters, because if you look at most leak rates in gasket standards, it is done by milligrams per second per OD of the gasket in millimeters. So we kept it consistent with that. And these are the results. So unsurprisingly, the only true, I say true full face gasket that wasn't an elastomer is the only one that failed. So the molded ePTFE, again, has a much lower minimum gasket stress than even expanded PTFE, but even with that, in a standard full face design, it failed the liquid leak test at both 35 and 40 foot-pounds. For those asking, it did leak from all 3 flanges very slightly. It wasn't spewing, but any sort of leakage is a failure. The other thing you'll note is that all of the other quote-unquote engineered gaskets that are designed specifically for this purpose did perform better than the full-face elastomer gasket, which again, up until this point, is what typically has been used. So not only do they help with the mechanical aspects or reduce some of the mechanical downsides of using an elastomer gasket, they actually seal tighter as well. When you dig down into a little bit further, and this graph on the right, I really wish I could update for you because we're working on this right now, but I'll point out that for the hex profile gaskets and for the elastomer gasket with the PTFE envelope on the ID, we are working on a way to calculate the effective gasket stress for both of those, because we know that the entire area of the gasket can't be used when we're calculating the gasket stress, or I guess the effective gasket stress, because you do have that point loading on those. It is very difficult to calculate. So for these purposes, we did use the full area of the gasket on both of those, which skews the graph a little bit, but generally speaking, you can see as you increase the effective gasket stress, you are decreasing the leak rate. The expanded PTFE with the insert performed by far the best, about 10 times better than the next closest. The rest, besides, again, the one that failed, were all in the same, I guess, standard deviation in terms of leak rates, although you can see when you go from like the hex profile filled PTFE in the full face design to the reduced area, you're just reducing that area of the gasket and going to that one piece reduced area design, you're cutting the leak rate just about in half. Same with the elastomer full face and the elastomer reduced area, you're cutting that leak rate in half by essentially cutting the area in half. In conclusion, what this means is elastomers are very good sealing materials in a lot of applications. They are not great for bolted flange connections. In this particular applications, there are a lot of options out there. The most important thing is do not use any other just standard sheet cut material in a full face design. You will have a leak, or you will break your flanges trying to fix that leak. There's a few different things. It's a combination of material reducing the overall area and also applying point loads onto the gasket itself that all contribute. When it comes into temperature and thermal cycling, which is the next step of the testing for us, is to basically be able to either have heat trace on the FRP piping and cycle it to see how the gaskets perform with thermal cycling, or pump heated fluid through the piping and test it that way. But we're looking at that now to further compare their performance in terms of thermal cycling. But if you have thermal cycling, that's something you need to take into account, because just a filled PTFE material will start to cold flow over time without anything to help mitigate that. Same with mechanical vibrations. Those will all contribute to your cold flow, unless you have something like the live loaded spring or the elastomer on the one with the molded PTFE center that's going to sort of resist those external loads. References. So we've written 2 PVP papers on this. The second one is just the inclusion of more materials, and the original one, which is sort of a proof of concept for us. We have a table in the back, and if anybody wants these PVP papers, I can send them to you. The second one, actually, I think PVP is next month or 2 months from now, July. So I don't think we're allowed to send it to you until technically they have the conference. But so we'll sit on that one for a couple months and then send it to whoever wants, and then the ASTM spec as well.